Hello, and thanks for joining us for Phosphorus Science Now. I'm Matt Scholz with the Sustainable Phosphorus Alliance, and today I'm joined by Dr. Céline Vaneeckhaute from Université Laval in Quebec. She's written a paper in waste management entitled Nutrient Recovery from Digested Waste towards a generic roadmap for setting up an optimal treatment train. I thought this would be a good paper to cover because we have a lot of stakeholders who are interested in recycling waste and recovering the nutrients in doing so. And I think Céline has put together a nice decision tree and set of guidelines for helping people who wish to do this put together an effective set of unit processes that fit the context in which they're operating. And so, Céline, I'd like to first thank you for showing up and welcome you to Phosphorus Science Now.
Thank you, Matthew. Thank you very much for the invitation. So yeah, basically it's a paper that was created with a very international team. And it's actually, basically the four co-authors that we have here were all my PhD supervisors. We talk about, so Dr. Evangelina Bedia, she's from industry, so Primodal. And then we have two co-authors from Ghent University, Dr. Erik Meers and Dr. Philippe Tak, and one co-author from Université Laval in Quebec. So that's Professor Peter van der Rollegem. And myself, Of course.
And who funded the research?
It was funded. It was a research funded by the Natural Science and Engineering Council of Canada in joint cooperation with the Quebec government, actually, and also a part was financed by the company Primodal.
So, Céline, can you tell us a little bit about the motivation for this research and why you undertook it?
The motivation comes from the requests from industry and municipalities. Well, we all have new regulations so that we have to treat our organic waste. And one treatment that is possible is, for instance, anaerobic digestion. So it's implemented quite a lot now for organic waste management. So we talk here about, for example, sewage sludge from wastewater treatment plants, also food waste, for instance, but it could also be more agricultural waste, such as manure. So the waste streams go in an anaerobic reactor. It's like a fermentation, and then we can produce biogas that can be used, for instance, to produce electricity or heat, or also even biofuels. And then, what is left is the digestate that we call it. It's very rich in nutrients still, but it's also very liquid. So it often causes problems to dispose of as such in its crude form, actually. So that is why the last decade, actually, multiple technologies for treatment of the digestate have been developed. And usually we start with a mechanical separation so as to produce like a solid fraction that is more rich in organic matter, phosphorus, calcium, and magnesium. And that can be dried or composted and used as a soil amendment in agriculture. So it can be transported further away as well. But what is left is a liquid fraction that is actually pretty rich in nitrogen, potassium, also still has dissolved phosphorus in there. And there we have a high potential for nutrient recovery. So when we talk here about nutrient recovery, we talk about recovery in a concentrated form. For example, mineral fertilizers that can replace actually the traditionally used synthetic fertilizers that we have today. Over the last decade as well, so a lot of nutrient recovery processes have been, they have been starting to develop. And here I show you, this is a review that we made, a bit with the same co-authors. It's on nutrient recovery technology, so it's a technology review and a product classification. And based on this review, we classified struvite precipitation, ammonia stripping, and acidic air scrubbing to produce ammonium sulfate, actually, and also the standard solid-liquid separation as most established technologies to date. So these are like the technologies that are already operational at full scale and that have shown to be economically feasible as well. So struvite is more like a crystal fertilizer, and then from ammonia stripping and acidic air scrubbing, there we have like an ammonium sulfate solution more.
Okay, great. So can you walk us through then, what a treatment train looks like for these resources?
Yeah, so exactly. So here we see, for instance, a treatment train for nutrient recovery. So we can have an anaerobic digester upstream. But then downstream, so once we have the digestate, we can have, for example, precipitation to produce the struvite, and then we can have a stripper and a scrubber to recover the nitrogen. Because if you produce struvite, it's a magnesium ammonium phosphate, but usually you don't capture all the nitrogen, so you could combine both of them. Now, this treatment train brings us to the main problem and the main reason and motivation why we did this research. So the fact is actually that we see while working with industries, municipalities who implement these systems, that the optimal combination of these unit processes are different for each waste flow. So we talk about, well, I mentioned a couple of waste flows just before, but for each specific waste stream from a particular industry or a particular municipality. So the characteristics are so different that also the technology choice becomes difficult because it's not easy to compare with other situations. So our main driver here as a research question was, what is the optimal combination now of unit processes, and what are the optimal operating conditions if we have like a particular waste streams and we want to maximize resource recovery, so both nutrients and energy recovery, and also product quality, while minimizing energy and chemical requirements actually.
So great, Céline. So how did you go about tackling this problem?
Yeah, well, this brings us actually to the objectives of this paper. We thought like it could be interesting to have like a roadmap, to provide a roadmap to the industries, to municipalities, to guide them in setting up their nutrient recovery treatment trains. And basically we saw that the main influencing factors are the local fertilizer regulations, also so fertilizer markets, so which products are of interest in the region, and the waste characterization. So we wanted to develop a roadmap as function of these three influencing factors. Well, to talk a bit about how we did that, basically we have a lot of data ourselves. So we did field trials with different recovered products, so the ones I discussed before. We also did greenhouse trials. We looked into literature, so for of course to use work of other authors as well. And on the other hand, we developed also a nutrient recovery model library. So there's another paper published on that. So it's actually a process model library with which we did sensitivity analysis to see which factors influence most process outcomes. So like the struvite production, for instance, or the biogas production. And then besides all of that, so we also had a lot of contact with multiple technology providers in the field. So they gave us a lot of full-scale operational experience for these processes and data as well. So as such, we really obtained like a good knowledge and understanding of these processes and of the product quality as well.
Okay, great. And it looks like you have a case study for us too. Can you walk us through one of these decision trees that you've developed?
Yeah, so if you look at the paper, so you will see that the roadmap, it's pretty large, so it can result in different configurations. So yeah, I wanted with you just to show you one potential configuration using a case study, and it's actually a case study for Quebec City that we developed. So basically the roadmap presents three different steps so that the user should walk through. So the first one is the user will need to set up a bio-based fertilization strategy as function of the fertilizer regulation. So basically here what we want to do is to see which products are of interest in the region under study. So which products should we recover and have a market in the region. So first question that one should ask himself is, are we in a phosphorus saturated region here? And for Quebec, actually, so we have a lot of phosphorus saturated soils in Quebec. So here for us, that is the case, which means that actually phosphorus becomes limiting factor if you want to apply fertilizers. So what does that exactly mean? So if phosphorus is a limiting factor, that will mean that, you know, you can not exceed a certain phosphorus standards, and that standards will be more important than the nitrogen standards. So this is a bit material for agronomics, but yeah, it is important. So if phosphorus is a limiting factor, then then we recommend with the roadmap to add a mechanical solid-liquid separation for the digestate. So the solid fraction, which will be rich in phosphorus, you can then dry or compost and transport it further away to a non-phosphorus saturated region actually. Liquid fraction could be used locally because it also contains like nitrogen and it's phosphorus poor, so it could be locally in addition or as a complement to manure, for instance, so as a base fertilizer, an organic fertilizer. So we could use it up to the phosphorus standards, the regulatory standards, so the recommendations. And then after that, we can add mineral nitrogen fertilizer, which could be the ammonium sulfate, up to the nitrogen standard for the mineral fertilizer. So this is what we see here. So in green, we see the potential products that can be of interest. So it's ammonium sulfate, the liquid digestate, and also I added here struvite, because in some cases, if we can still recover struvite from the liquid fraction, it can be of interest, well, either to transport it or either also to use it to fill up that phosphorus fertilizer recommendation. Of course, so once we have decided which products can be of interest, then we of course have to see if the technology to produce those products can also be feasible for the waste treatment facility that we have actually. So for example, if you look at Quebec City, so here we are building a large anaerobic digestion plant, but so it's not operational yet, but the predictions that we have for the Digestate is that the phosphorus load is lower than 80 kilograms a day. And this is actually here a standard that we have from struvite producing companies that say, like, if it's lower than 80 kilograms per day, then it's actually not feasible to produce struvite on your liquid fraction. So this is actually the case for Quebec City. So this is what. So they're not going to implement this struvite recovery, but their concentration of nitrogen, on the other hand, in the liquid digestate will be higher than 400 to 500 milligrams per liter, and that's about the standards for ammonium sulfate production to become feasible. So here, in this case, nitrogen recovery is feasible and will be used. So this is basically the second step, so to evaluate the feasibility. And once we know which technologies are feasible, so in this case, it's clearly ammonium sulfate recovery, well, then we use a more detailed conceptual algorithm for designing the optimal treatment train. So here, of course, this is a schematic overview, pretty much simplified. If we see, so on top here, that the nitrogen is higher than 500 milligrams per liter. If that is the case, so it is the case for Quebec City, then we can have multiple pre-treatments actually, that, as we see here. So first we have the total suspended solid content that needs to be checked. You also need to check the chloride content and the alkalinity in this case to see, like, if you need additional technologies as pre-treatment to the real stripping and nitrogen stripping and absorption technology actually. So, and then if we do the nitrogen stripping and absorption, so usually we want to have an ammonium sulfate concentration of 25 to 40%. So once we reach that, so here we see the yes, so for fertilizer market, so your product is ready. And if you didn't reach your effluent discharge or reuse level with achieving that, so you can add a final effluent treatment to reach the discharge or reuse level. So yeah, this is the specific case for Quebec City that we saw here. Here we have a little summary of the optimal configuration. So in the first step, we saw that the soils in Quebec City are saturated in phosphorus. So the main products of interest are ammonium sulfate, liquid digestate, and potentially struvite, so based on the roadmap. In the second phase, so we evaluated the feasibility, and we saw that recovery of phosphorus is not feasible, so as struvite for Quebec City, but recovery of nitrogen is feasible. And so the optimal treatment train that we proposed is to have a solid liquid phase separation to produce the liquid digestate, then a pre-treatment if needed, of course, and then ammonia stripping and absorption to produce the ammonium sulfate. And this is actually the case that will also be implemented at Quebec City now.
Okay, great. So you've got this great case study of what you would, how the roadmap applies to this specific case of Quebec City, but then you've expanded that out to create a generic roadmap that people can use.
Yeah, so basically what we see in the paper, so it's much larger than the specific case, of course. So it's applicable to every kind of situation, but it's still for digested waste. So it's for treatment of digestate, but multiple configurations are possible, as you will see in the roadmap paper. And that's why we also have actually an Excel tool available that facilitates the use of this roadmap. So you just have to put in some inputs, and then we provide you easily with the results. So you don't have to walk through the roadmap actually yourself.
where's this going to go? Where's this research going to lead from here?
So this tool is now available, but of course we always want to go further, right? So basically, well, we had requests of multiple people, industries, and so on to extend this roadmap so as to also include actually the collection of the waste material, then the transport to the waste treatment plants, and then the transport to for example, the agricultural field. So for the product distribution, because we see, well, it's all influencing each other. So we want to make more holistic decisions of where, for example, should we place our anaerobic digestion plant, and also, for example, where should we distribute our end products. So here in this tool, so this will include our roadmap tool that we already have, so with the mathematical models included, but it will be coupled actually to a geographical information system, so to include the whole transport network as well. And then we are extending it also with cost calculations and with greenhouse gas calculations at the same time.
That's fantastic. And so the plan is then to have a website or something where people can input this information?
Well, yeah, the plan is actually, so this tool, so it's in cooperation with companies. So actually this tool will be commercialized afterwards.
Well, that was a great summary, Céline, and thanks for walking us through it. And thanks for taking the time for joining us today.
Well, thank you for the invitation. Hope you enjoyed it.
I did, thank you.